Hi everyone. So in this short video, we'll try to understand some of the basics of electromagnetic induction. Mainly, we will be studying about Faraday's experiment. So around 1830s, it was known that if you have a current carrying conductor, around that you will see a magnetic field. But can magnetic field produce electric current? It was known that an electric current carrying conductor will produce a magnetic field. Is the other way possible? And this is where Faraday's experiment come in and prove the other way is also possible. And this is one of the most beautiful experiments out there in physics, but yet very simple to understand. And thanks to Faraday, who noted all of this down very meticulously so that we understand these things way, way better now. So let's get started, right? So let's understand the first experiment that Faraday did. See, on the left side, you see there is a coil which is connected to a galvanometer, a set of coils connected to a galvanometer. There is no source, right? It is just coils with the galvanometer. There's no battery or there is no AC supply, anything to that coil. And now on the right side, you see there is a magnetic field, which is produced by a magnet. And he starts moving this magnet towards the coil. And surprise, surprise, he sees some deflection in the galvanometer. That means, so the moving magnetic field was somehow producing current in the coil. So then once he moves them away, the deflection was happening in the other direction. And when he keeps this magnet inside the coil, nothing was happening. So only when he moved the magnet, he could see some deflection in the coil, or in the galvanometer connected to the coil. So let's see this in a quick simulation, which will help you understand better, right? So now I have a magnet here, which is in front of a coil, which is connected to a meter, which measures if there is current in this coil. So look what happens, right? If I start moving, there is a slow current. These blue dots you see is represents electrons. You start seeing them moving, and also you see a deflection in the voltmeter there, right? So now I quickly move, again, you see the deflection. And if I move forward, the deflection is towards the left, and I move backwards, the deflection is towards the right, right? You clearly see this. But check this out. So if I keep this in between the coil, what happens? There is no movement at all. So that means just keeping the magnet there didn't help, but only moving the magnet was what was creating this deflection of the galvanometer. So this was his first experiment. So let's go to the second one now. So now what Faraday did is, so this is brilliant, right? So he took another set of coils connected to a battery. So now this is equivalent to a magnet, but this is not magnet itself. So that shows us that was nothing special with the magnetic material itself, right? So now he takes this coil, which are connected to a battery, which is C2, what's what you see in the image, and he moves this set of coils connected to a battery towards the C1, which is exactly same as the previous setup, and he sees the same outcome. So the galvanometer deflects when it's coming closer, and when it's going further, the galvanometer deflects in the opposite direction. Again, let's quickly see this also in simulation, right? We have the setup here. We have a coil which is connected to a battery, and there is current through it on the left side. And on the right side, we have a bunch of coils, and then there is connected to a voltmeter. So right now, you don't see any deflection. Let me start moving the left coil towards the right. So you slowly see some movement there. Let me increase the pace. Again, I move forward, the deflection is towards back, and then I go back, and the deflection is to the opposite direction. Again, see what happens if I keep it inside. Nothing happens. So it seems that the motion of one or magnet or the set of coils is important. So what is this motion? By moving this, what is happening? Right? So Faraday is trying to understand by variations of experiments, right? So this is the second one. He just replaces the magnet with set of coils with attached to a battery, and he sees the exact same outcome. Now let's go to the third one. So the third one is exactly same setup as the second one, but only difference is instead of moving the coils, what he's doing is he's connected C2, which you see in the image, to a switch now. So he turns on the switch, and then he turns off the switch. So this is brilliant because now he's showing it has nothing to do with the movement of the coils at all. You can still produce the current without moving C2. So that, let me quickly show you that as well, right? So now let me position these two, see both the coils, and all I have to do is, so let me, yeah, so now there is no current in the left side of the coil. I'll quickly increase it to the 10. That means I'll quickly switch on. So you will see some deflection in the voltage. Let's see. So if we do it again. So there's a very slight deflection, right? So that's what Faraday was able to see, right? So these are the three experiments, three very simple experiments. So in the third experiment, what was important is that there is no motion of the coil, but somehow there is still current produced in the C1. So then what is that is making this current produced in the coil C1? So it's not the magnet itself, it's not the movement itself, right? So interesting. So Faraday came to an understanding that there is this magnetic field around the magnet and which is changing with the coil. And every time the amount of magnetic field that is changing with the coil, that is what is causing the current to be produced inside the coil C1, right? So let's quickly understand some terminologies here so that we can define what is magnetic field and magnetic flux, and then we also understand the Faraday's law by definition, right? What is magnetic flux? Very similar to electric flux. So magnetic flux is simply the amount of magnetic field lines passing through any given surface. So if you see phi B is equal to B dot A. B is the magnetic field intensity and A is the area, and it's a dot product. So that means it's the perpendicular lines that matter. It's not parallel lines. So let me create a quick example. So I have a book here, right? So and I have magnetic fields passing through this. But if I keep the book like this, when the magnetic fields are like this, so then there is no flux passing through this. So that means magnetic flux passing through this surface is zero. But now if the field is like this, so then there is a lot of magnetic fields passing through this. So that means there is magnetic flux through this surface, right? So it's just the amount of magnetic field passing through any given surface is called magnetic flux. And let's finally quickly understand the definition of Faraday's law of induction, right? So the magnitude of EMF induced. So EMF means electromotive force. That is what makes the electrons move around. So it has nothing to do with the force. It's just a nomenclature. It's the voltage or the force that creates the electrons move, right? That's why it was called electromotive force. So he's saying the magnitude of induced EMF in a circuit is equal to rate of change of magnetic flux. So what does that mean? Rate of change of magnetic flux, right? Let's quickly go back to our simulation where we saw this, right? So let me quickly check the field, right? Okay, so now you see there is electric field around this magnet, right? So, and there is only a fixed set of magnetic field lines passing through the coil. So I have to change this flux through this coil. So only then there will be an EMF induced or an voltage induced. So let me quickly move this. The motion of a magnet is changing the flux that is passing through this coil or induced in this coil. So this change in magnetic field or magnetic flux associated with this coil is what is producing the current. So that's all the Faraday's law is. So now he's saying how magnetic field is connected back to electricity, right? So he's saying every time you change this magnetic field associated with any surface, so then suddenly there could be a current in that circuit. So and it's brilliant. So in electricity, you don't have to move it. It just has to be a wire, and there is a magnetic field all the time. But in case of magnetic field to produce electric field, you have to change the magnetic field. So the rate of change, how fast you change, will determine how much the electricity is produced in this. So that's this equation. If you see, it's rate of change of magnetic flux associated with any surface that is producing the EMF. So you also see the negative direction, negative sign in the equation. So that is because of Lenz's law, which we'll talk about in the upcoming videos. Thank you for watching, and we'll see you in the next one.